Okay, we're going to do a short video about the derivatives of inverse trig functions. I know you're excited about that. And then related rates. So that'll make the next class go a little bit better, I think, if we kind of go over these pretty quick. All right, so I'm going to kind of hopefully share my screen. All right, and we'll see what happens. Okay, so derivatives of inverse functions, like inverse trig functions, and then related rates. Now, in your books, there are these formulas, okay? So this is out of section, I think it's 3.6, okay? So all I did was just take a picture to make sure that we're clear, okay? So these are the only formulas that I will give you on a test, okay? So you do not have to memorize these inverse trig derivative formulas, right? Yes, you're welcome, okay? But you do have to know how to use them. So notice this is not really U substitution. Unfortunately, they use the letter U, so it's a little confusing. But U is what follows like arcsine or arctan or arcsecant, arccosine, arccotangent, arccosecant. So the first thing you want to do is identify what your U is. And so for the derivative of that, your denominator is just the square root of 1 minus whatever your U was squared. And then on the top, you put the derivative of U. All right, so I'm just going to go work a couple just to kind of make sure we're clear. Okay. All right, look at this one. So it's asking you to find your function's arcsine of 3x plus 5. So it's only going to take you about 3 seconds to go to the side and write down what U is. And U is what follows arcsine. So do you see that your U is 3x plus 5? Okay. And so the derivative of that would just be 3. So I copied again from that previous slide, I copied down my formula for arcsine because this would be written on the board for you. So on the bottom, you put the square root of 1 minus U squared. So I put the square root of 1 minus, and so right there, there's my U. All right, but it's squared according to the formula. And on the top, you have the derivative of U. So the derivative of that thing was 3, so 3 went on the top. So that's what you would have. 3 over that root would be your derivative. Okay, now it's also going to show up in the middle of other things, like your function's x squared times the arctan of 5x. So do you recognize if they want you to take the derivative, you've got to use your product rule because there's understood to be a multiplication right there. Okay, so remember your product is the first, so I just copy down x squared times the derivative of the second. So I've got to do the derivative of an inverse trig function. So this would be written on the board, the derivative of arctan U. On the bottom, it's not a root, it's just 1 plus U squared, and on the top is the derivative of U. So like I said, it's going to take you 3 seconds to go up here and write down what your U is. Your U is 5x. So that denominator is 1 plus, so there I'll slide in my U, but I've got to square it. Then on the top, I need the derivative of U. So what's the derivative of your U? The derivative of 5x is just 5. So that's the first times the derivative of the second, and then plus, remember you copy down the second, and then you do the derivative of the first. So the derivative of x squared, of course, is just 2x. And then you just simplify it. 5 times x squared is 5x squared. If you square 5x, you got to square the 5 and the x, so that's why I have 25x squared. And then I move the 2x in front just so you're not tempted to multiply that 2x by that 5x because you're not paying attention. Okay? So as far as inverse trig derivatives go, all I expect you to be able to do is to, if you have the formula given to you, which you will, is to be able to use the formula. Okay, so not really much new there. Now what I want to look at are related rates. Now related rates are a certain kind of word problem. Okay, so these are kind of the steps for related rates. They put some steps in your book. And they're good. Mine are just the same. They're just worded a little differently, maybe a little more specifically. So anytime I work a word problem, I'm going to basically draw a picture because I'm a visual learner. So if you're a visual learner, pictures help. So if I can draw a picture, I will. If I can't, then I won't. All right. Then just to be organized, you need to write down what you're given in the word problem and what you're asked to find. And in these related rate problems, they're going to be talking about rates of change. And that's going to imply derivative. So kind of be looking for where it says a rate of change. Okay. Then you're going to look at the picture that you drew, what you've written down next to given, and what you've written down next to find, and you're going to come up with some formula, some equation should kind of pop up for you. All right, so you're going to write that equation down. Now you're going to take the derivative of that equation implicitly. But this time, instead of having dx on the bottom all the time, you're going to have dt, because these are rates. So it's always something compared to time, you know. Rate is distance divided by time, you know. So instead of having dx on the bottom, you're going to have dt on the bottom. So implicit differentiation, that chain rule, with dt on the bottom. Then you're going to substitute in all the things that you know from your given, and you're going to solve for your unknown, which hopefully is what you were asked to find. So let me kind of go, you can pause it and take notes right here. I'd pause and I would write this down in my notes so that you can look at it before you go to the next slide, because you're going to need to be looking at the steps when we get to the example that's next. All right, let's see if we can get it to do. All right, so let's go to the example. Look what this one says. A rock is dropped into a pond, forming concentric circles. Now, concentric circles are just circles inside of other circles, okay? So you've seen them before. Think of a bullseye. You know, like if you've got a target, you've got circles inside of circles. So, you know, when you drop that rock in, you start getting those ripples going out in the shape of a circle. And it says the radius of the biggest circle, so the radius of the outer ripple, is increasing at a constant rate. See, remember I told you it's going to have something to do with rate, of 1 foot per second. Okay, then it says they're going to freeze it when the radius of that circle, that big circle, is 4 feet. They freeze it, and they want to know at what rate is the total area of the disturbed water changing. So I went back and looked to see if I could draw a picture, and it said I've got circles, so I drew a picture of a circle. All right, they told me to call the radius r, so that's why I labeled it r. If they hadn't told me, you could have called it x, whatever you want to call it. Okay. Now, they say that it's increasing at a rate. Now, what is increasing? Radius is increasing. So this is a change in the radius with respect to time. So that's why I put dr over dt. All right, so dr, because it's the radius. They said the radius is increasing, so that's why it's positive. It's getting bigger at 1 foot per second. So that radius is growing at about 1 foot per second. All right. Then it freezes it when the radius is 4 feet. So that's something else that I'm given. I'm given the radius when they freeze it, and I'm given the rate the radius is growing. Then it says at what rate, so they're asking me to find a rate, is the area changing? So they're asking me to find the change in the area. So that's why I put dA to dt. I put dA for area. Okay. So that's what I mean by, you know, draw your picture on step 1, write down your given and your find on step 2. All right. Then the next step, remember your next step, step 3 said that you're supposed to look at your picture and your given and your find and come up with some formula. So I'm looking at a picture of a circle. I'm looking at radii here, and I'm looking at area here. So the formula that pops into my head then is the area of a circle. So I wrote down the formula for the area of a circle, and I would expect you to know the area of a circle. Okay. Then the next step is going to tell you to take the derivative implicitly with respect to t on both sides. All right. So what's the derivative of a single letter like a? It's 1. Now, what variable are you looking at? You're looking at a, so it's dA. Remember, all these are over dt because they're rates. So they're with respect to time. Pi is a number. So we don't touch numbers in front. Even if it's pi squared, we don't touch it. Pi's are just numbers, okay? But the derivative of r squared is going to be 2r. Now, what letter, what variable are you looking at? You're looking at r, so it's dr over dt. So implicit with respect to t this time. Then I just clean it up a little bit, so that's just dA over dt. All right. I like numbers, I like variables, you know, kind of numbers in front, so I put 2 pi. Now, my radius, they're freezing when my radius is 4, so I plugged in 4 for that r. And then I know what dr over dt is. It's 1 foot per second. So I took my radius and substituted in. All right, there's my 4 feet. I took my change in the radius and I plugged that in. So they told me it was 1 foot per second. So 4 times 2 gives me 8 pi, and a foot times a foot is a square foot. So it shouldn't surprise you that the change in area is in square units, because area is always measured in square units. So when the radius is growing at this rate, when you freeze it at this length, then the area is changing at 8 pi square feet per second. Remember, pi is a little more than 3, so it's changing a little more than 24 square feet per second as this thing's growing. Okay? So hopefully that's making a little bit of sense about those steps. All right, let's go work another one. One more. All right, look at this one. All right, it says air is being pumped into a spherical balloon. So I'm blowing up a balloon at a rate of 4 5/10 cubic feet per minute. Find the rate of change, the radius of the balloon when the radius is 2 feet. So it tells me that I'm blowing up a balloon. So air is being pumped inside of a balloon. And it tells you can get lots of shapes of balloons. You can have tubes or round spheres, or they have all kind of hearts. You can have all different kind of shapes. So they tell me my balloon's in the shape of a sphere. So that's why, remember, Steph wants to draw a picture, so I drew a picture of the sphere. Now, they didn't tell me what to call the radius, so I just called it R out of habit for radius. Remember, step 2, write down your given. It says air is being pumped into the balloon at this rate. Now think about it. When you're blowing air in a balloon, doesn't the air go on the inside? And isn't a balloon three-dimensional? A sphere is three-dimensional. So what do you call the inside of a three-dimensional figure? Isn't that the volume? All right. So that's why I said dV to dt then is 4 5/10 cubic feet per minute. The other hint was it was cubic, and volume's measured in cubic units. So that's why I put dV to dt. Then it said find the rate of change of the radius. Find the rate of change derivative of the radius. So that want me to find dr to dt. And they're freezing it when the radius is 2 feet. So that's another given. So remember that step says look at your picture, your given, and your find, and try to come up with some formula. So I'm looking at the picture of a sphere. It's talking about volume, that V is volume and a radius. So I know I've got it memorized. You might have to look it up. On the back flap of your calculus book, there's some geometry formulas, or you could Google it. All right, the volume of the sphere is 4/3 pi r cubed. So that's what it means by look at your shape, look at your picture, look at your given, look at your find, and try to come up with a formula. Now, the one we work in class, when you come to class, the formula won't be quite as obvious. So sometimes it's really obvious, and sometimes you have to think about it a little bit. All right. When you get your formula, take the derivative with respect to t. So you're doing implicit differentiation. So the derivative of a single letter like V is 1. You're looking at V, so it's dV over dt. 4/3 is a number and pi is a number, so I don't touch numbers in front. I just copy them down. But the derivative of r cubed is going to be 3r squared. Now, what's your variable? R, so it's dr on the top, and it's always dt on the bottom. Okay, when we're doing related rates. Okay. So basically, I cleaned it up because that 3 and that 3 are going to divide out. All right, so they divided out. That one divided out with that one to a 1. 1 times dV over dt is dV over dt, so I was left with this. So I plug in what I know. I know this time I know dV to dt. So I plugged in dV to dt, 4 5/10. Now you can put cubic feet. Remember, it's going to be cubic feet. I'm going to make sure we're clear about something. You don't have to put the units in your scratch work, but you do have to put them in the answer. So that's cubic feet, this time per minute. Okay. So if you want to put the cubic feet per minute there, if you're afraid you'll forget, then do that. All right. Then I've got my 4 and my pi. Now wait, I've got my r. Now what's my r? My r is, my radius is 2 feet. And again, right there, if you want to put feet, you can do that. Okay, if you're afraid you're going to forget. Okay. Remember what we have to do first, we have to do our powers. So 2 squared is 4. Well, 4 times 4 is 16. So I've got 16 pi. Now notice, that would be 2 feet, so that feet would get squared. So again, if you're afraid you're going to forget, you can right there put square feet. You don't have to, but you could. Because everything in the parentheses, remember, gets squared, and it was 2 feet in that parenthesis. Now this time I'm trying to solve for dr over dt. So that's what I'm looking for. That's what it says to find. So I've got to get rid of this 16 pi. Well, how do you get rid of 16 pi? Don't you undo multiplication by division? So if I divide this side by 16 pi, that goes out and leaves me dr over dt, and I divide it by 16 pi over here. But think about it. I'm dividing by 16 pi square feet per minute. Okay. So do you understand that when you take cubic feet and divide by square feet, you would just get plain feet? A cubic divided by squared is a linear, all right? But you should know it's going to be linear anyway because it's a radius. A radius is measured in just linear units. So you should know that it's that feet per minute anyway, just 1 foot, because it's linear. So I don't care if you put it in the scratch work, but you've got to put it in your answer. So that would be an exact answer. If I wanted an exact answer, and that would be a decimal approximation, you can double check me. Okay. So that's basically how we're going to do related rates. I'll give you a few simple ones to look at, and then maybe for homework. And then in class, we're going to work 1 or 2 more that are not quite as obvious. Okay. And then we're going to move on to extrema. All right. And you'll have a video about extrema next. Okay. So try the homework. Let me know if you have any questions, and I'll see you in class.